Welcome everyone to another lesson on Khadija Academy. Before we start this lesson, hit the subscribe button, the notification bell, and the like button for the YouTube algorithm. Now let's go and start our lesson. Okay, so let's understand now how can we generate the switching signals of our inverter. So what we are going to do is that number one, we have in this video or in the technique which we are going to use is called the sinusoidal pulse width modulation, sinusoidal BWM. In this case, we will compare with the carrier wave. So what we do is that remember that we have VA reference, VB reference, and VC reference. What we would like to do is that VA reference will be a sine wave like this one. We will compare this one. This wave is called the modulating wave. We will compare it with a triangular wave like this one, which has a certain frequency, or another one like sawtooth like this one, which is also having a certain frequency. Now you have to know that more frequency of the triangular wave or sawtooth, more the harmonics will go down. Okay, harmonics will go down. However, or more sinusoidal wave will be given. However, at the same time, the higher the frequency, more switching losses occurring. So we have more switching losses or more power losses, more heat generated. This is just in general about these switches. What is the frequency of these carriers? It can be, for example, 1 kilohertz, 5 kilohertz, and etc. I usually use 1 kilohertz in my applications. Rarely I have used 5 kilohertz. Okay. So what you will see right now is an example of what happens exactly. So let's say the reference wave or the modulating wave, the waves that I need is a sine wave with this waveform, okay, for one cycle. And we have our this one, which is the carrier wave. So we have a carrier here, which is a sawtooth or here a triangular wave. By comparing these two, I can give the switching action. Okay, so what happens exactly? Let's look here. So whenever the carrier, let's type it here, if carrier greater than modulating, then output would be equal to 0 for, let's say, S1. Okay, so we are talking about S1 and S4 for phase A. Okay, for example, okay, so we have upper switch and lower switch. So if carrier greater than modulating, okay, the carrier signal like this one has a magnitude greater than the modulating, then the output will be equal to 0, which means S4 will be on. So it means that the upper switch will be off and the lower switch will be on. An example for this, you will see that here at this point here, you can see carrier, which is this one, greater than the modulating signal. Value here, carrier greater than the modulating. So S1 is 0 and S4 will be 1, which means the output will be negative. Why? Because in this case, S4 is connected to the negative of our supply. We will see this more in the next slides. So what you will see is that at this region here, you can see that output is negative pulse. Again, let's look at the next one here. You can see this one here is the opposite. If carrier less than modulating or the modulating signal greater than the carrier, then output will be 1, which means S1 will be on and S4 will be off. which means S1 is connected to the positive of the supply. So what you will see in this region here, you will see that this from here to here. In this region, the blue one, which is a modulating signal, is greater than this triangular wave. So from here to here, from here to here, we will have a positive supply. So you'll see that the out here is positive. Okay, similarly, as we continue all of this, you will find that we will have the final pulses that you will see here. These pulses representing the switching action happening on our switches. Let's look at it with a triangular wave again, but for a three-phase system. So assuming that we have a three-phase, A, B, C, three phases here. So what we do is that we have a triangular wave like this. Again, triangular wave. The same exact, let's take any of these waves. For example, the red one. So you'll see that the red one from here until here. Okay, let's type it. From this point, okay, until here. Okay, from here, okay, there is a little bit part here, okay, which is smaller. Okay, we can just neglect this part, okay, assuming that this red is greater than all of this triangular wave here. So you can see that this modulating signal is greater than carrier signal. So the output is almost on in all of this region. There is a small pulse here, a zero pulse or a negative pulse, because in this part it is just smaller than the triangle. Okay, so let's just take another one here. For example, this part, you can see in this part the carrier signal greater than the modulating signal. This is translated from here to here, go down here, you can see from here to here. This part is exactly this part at which carrier greater than modulating signal, so it will be off. Here we're talking about S1, so it will be on, off, and etc. Similarly for the second sine wave representing VB, third one representing VC. Okay, so this is translated in the end into pulses that we would like to reach in the end. These sine waves, these pulses translates to these waves. Okay, so let's say I'm going to look at one wave, just one wave, to make it more clear. For example, if we take this switch S1 and S4, so we have upper switch S1 and lower switch S4. So we have our modulating wave, and this is the triangular carrier wave. Look carefully here. For example, between here until this point, you will see in this region that the carrier wave greater than modulation wave. So in this case, S1 will be equal to 0, which translates to S4 being 1, the complementary, as we learned before. So what you will see that the upper switch S1 in this region is translated into 0 value. 0 value. On the other hand, S4 will be the complementary. It will be 1. So what does this even mean? It means that S4, so look at this supply, S4 is on and S1 is off, which means that the VA, voltage A, is connected to negative of the supply. Okay, negative of the supply. Looking at another point, this one here, you'll see that this one here greater than the modulation index, modulating wave, greater than carrier wave in this region, which means that S1 will be on, and on the other hand, the complementary S4 will be 0. So looking it at this region here, going down here, this is a corresponding one. So on for S1 and S4 will be off. This is translated into like this. On, and this one is off, open circuits. You can see that VA is connected to positive of the supply. So using this, you sometimes switching on and off, on and off, on and off, and etc. Okay. If we're looking about a single phase system, and you will find a paper that I'm going to attach it to this course. For this one, we will have modulating a wave, blue one, purple one, for, or violet, whatever this color is, for A. Okay, and the yellow one for B. And we have here the triangular wave, which you can see here, okay, with a certain frequency. By comparing each of these waves, we have the gate switches. One for, so we have this one, we are controlling S1, and for B, we are controlling S3. And by knowing S1, S4 will be the complementary, right? Complementary of A. And S2 will be complementary of S3. Looking at this here, for example, you can see gate pulses of switch 1, which is S1, this switch. And this is the gating pulse of switch 3, this one. So by controlling switching of S1, we will get S4. And by controlling S3, we will get S2. Okay, so let's look at it. You have here, this one is for A. Okay, and if you compare these two together, you will find that there are regions at which A, like here, let's make it here like this, A greater than, or modulating index, modulating wave greater than carrier wave. So you'll see that this is corresponding to a period of on, as you can see here. For B, you will find the same periods at which it on. If you go down here, you will find a period which is on. Anyway, you will have these pulses. The output voltage which we are looking for is VAB, which is VAB is VA minus VB, line to line voltage. So VAB is simply VA minus VB. So we have these switches minus these switches, right? Because this representing VA and this representing VB. By subtracting these two together, you will have this final waveform, which is more clear for you now that this is a sine wave, right? A sine wave, but in the form of pulses. If you look at it, you can think of it like this. So as you can see here, if you look at this point, VA, this point is on, VB is on, then the output will be 0. If you would like to see it here, you can see it actually. Let's say S1 is on, so S1 is on, like this. And this one is on, S3 is on, like this. So what you will see is that A, like this, is a short circuit with B, making VAB equal to 0, as you can see here. If you took another point like this, you can see that here A is on, so S1 is on. And the second point here, this point S3 is 0, so this one is off. Meaning that when the S3 is off, it means that S2 will be on. We said that they are complementary of each other. So what you will see is that here, that VDC goes to A like this, goes all the way like this, and the return is back to supply from here. So what you will see is that VAB will be equal to VDC. So in this point, you will find that it is maximum. VDC is 100 volt. Okay, so it is equal to its supply voltage 100 volt. I hope you now understand how these pulses, how these comparison is translating into these pulses, and these pulses gives us the final waveform. Now I know your question will be, how can we even convert these voltages into sine wave? This is not a sine wave, this are group of pulses. So in the first case, which you have seen in the previous slide, you will find that the total harmonic distortion in the wave is 2%. You will find that we have, this is a fundamental frequency which we need, and you will find that there are other harmonics that are presented at a higher frequencies. So what we can do that is that we can eliminate the high frequency component. How can we even do this? By using a low pass filter. So this is the result, 2% harmonics, total harmonic distortion, without any kind of filter. If we use a filter, you can make almost all of these high frequency harmonics almost dead. So you will have almost the high frequency and another one here. But most of these frequencies or these waves are dead. So we'll find that the total harmonic distortion moved from 2% to 0.22%. How did they achieve this in this research work? By using an LC filter. We have many types of filters. Some of them are LC, LCL, and RL. Okay, all of these filters are used to eliminate or reduce the harmonics. The result will be like this. Instead of having these group of pulses like this, okay, you will have a final sine wave waveform, as you can see here. Now, of course, the amplitude itself is reduced from the 100 volt due to the presence of a filter that reduces the magnitude of the output waveform. However, in the end, we produced a pure sine wave that can be used for our applications. So I hope you now understand. If we get back all the way back here, you now understand that after taking VA, VB, VC, which are our three-phase sine waves shifted by 120 degrees, we can use a comparator by having two tools like this. By comparing this, we will have the switching signals for S1 and S4 will be the complementary. When this one is on, it will be off, it will be on, and etc. By giving these switches, you will get the final output voltage, and then we use a small filter or a low pass filter to eliminate the harmonics and get the sine wave. In the end, all of this, what we did here is called the scalar control or voltage control. We control the magnitude of the voltage and the phase in order to achieve our control objectives here. Thank you for watching this lesson. I would like to invite you to our academy, Khadija Academy Premium membership, which will help you learn more about electrical engineering. In this academy or in the academy membership, you will find that we'll have more than 100 courses in math, electrical engineering basics, power engineering career preparations. For example, we have electrical design, we have courses on electric circuits, power electronics, ETAB, MATLAB, solar energy, wave energy, wind energy, and much more. You can join our membership for just a small fee per month, or you can just have a lifetime access in which you will get all of current courses and classes, and you can have them forever. And not only this, but any new courses that will be created, you will be able to watch it for completely free. So what are the classes that I will learn in this membership? You will find different classes in electric circuits. You will find in transformers, magnetic circuits, machines, power electronics, load estimation, lighting design, lightning also design, earthing system, cables, generators, like current systems or low current systems, off-grid design, on-grid design. Very lots of classes and courses in different topics.